Hi all. As we learned in the previous video on Bayesian parameter estimation, if we are given a set of training data values where x is the input vector, y is the output vector, and a set of new input values, our job is to predict the output values. And to do that, we use basic concepts of probability theory. So essentially, probability of y tilde given x comma y comma x tilde is given as an integration of the probability of y tilde given x tilde given rho, where rho are the parameter values of our machine learning model, multiplied by the probability distribution of the parameter values given the training data values integrated over all possible values of rho. And that is what we do in Bayesian parameter estimation. But as I mentioned in that video, that this process is very complicated to perform for most real life problems. So in machine learning, from a practical perspective, we use a simplified approach. So what we do is that we estimate this quantity to be equal to the probability of y hat given x hat and some estimated value for rho. So this is what we do in practical machine learning exercise. And how do we choose this rho e? So this rho e is chosen to be the value of rho which maximizes this quantity. Okay, so what we do is that our rho e is equal to argmax. What that means is that the parameter value rho which maximizes this quantity. So this is what machine learning is basically all about, that to estimate this distribution and to find rho which maximizes the value for this distribution. So as I mentioned in the previous video, there are two ways of doing it. One is the MLE, which is the maximum likelihood estimate, and the MAP, which is the maximum a posteriori estimate. So in this video, we are going to focus on MLE, which is also a simpler method, and see how to do this computation of argmax of this distribution. Okay, so here we are going to use Bayes theorem once again, but in a slightly simplified manner. Not of course as simplified as our naive Bayes, but still simplified compared to Bayesian parameter estimation. So using Bayes theorem, what we have is that f of rho given x comma y is equal to the probability of y given x comma rho times the probability distribution of rho divided by the probability of y given x. So this thing is called the posterior estimate, because this is the estimate for rho after we have taken into account the values of x and y. This quantity f of rho is what is called the prior, and this quantity is what is called the likelihood. So this is the likelihood of getting an output y given the values of x and rho. So now because we are doing a maximum likelihood estimate, and the simplifying assumption is that we do not assume anything about f of rho. So in MLE, we take f of rho to be a uniform distribution, and so this goes out of our calculations. And as you know, the objective over here is to find an estimate for rho. The MLE estimate is equal to argmax over rho of the distribution f of rho given x comma y, and so this is equal to the argmax of this quantity over all possible values of rho. Now obviously p of y comma x does not depend on rho, and so this can be thrown out. In MLE, we are not assuming anything about f of rho, so this also goes out. So essentially what remains is that this is argmax over rho of the probability of y given x comma rho. So this is what we are going to compute. So this is our basic definition of the maximum likelihood estimation. So this is the definition of the maximum likelihood estimate, and this is where it gets its name from, because as you know that this quantity is called the likelihood. So we are ignoring everything else and we are just trying to maximize the likelihood of our training data values. So this is what we want to calculate and then use this to make our predictions for new data points. So now let's see how to actually do this. So now as I mentioned that you can't learn the parameter values just using one training data point. So now you have a large number of training data points, and so this x actually is x1, x2, x3 and so on, and y is again y1, y2, y3 and so on, with each xi and yi being vectors. Okay, so we are not going to worry too much about vector calculus because that is not our objective. We just want to understand the basic concept of how this method actually works. So our rho MLE is equal to argmax over rho probability of y given x comma rho, and because there are many training data points and we assume that all of them are independent, so in naive ways we assume that the parameter values are independent. So here we are not doing that. Here we are only assuming that the input data values are independent, which is a fair assumption to make. So this probability would actually be a product over all I of P of yi comma xi and rho. So now usually products are more complicated to handle, so what we are going to take is just a log of this function, and that does not change anything because if the function is maximized, its logarithm is also maximized. So this is equal to argmax of rho summation over all I log of probability of yi given xi comma rho. So now this quantity is called the log likelihood and can be denoted by LL. So this is what we are going to maximize in our maximum likelihood estimator. So this is a general concept of MLE, and now let's apply that to our favorite coin toss problem and see what estimate do we get for rho by using this method of maximum likelihood estimation. So now let's get back to our favorite problem of coin toss, and let's say that our rho is the probability of heads, and we denote heads by 1 and we denote tails by 0. So now we don't have a input value over here, we only have output because output only depends on the parameter, there is nothing else. So now our output values yi, they can be from 0 or 1. We don't have any input values over here because it is just a simple coin toss experiment. So we have the probability of heads, which is our parameter which we want to estimate, and we have the output values yi, which can be either 0, which means tail, or 1, which means head. So the probability of yi given rho is equal to rho to the power yi into 1 minus rho to the power 1 minus yi. So this is a very nice and compact way of incorporating the probability of both head and tail. How is that? Consider yi to be equal to 0. So now this is yi is 0, so rho power 0 becomes just unity. So this kind of goes away. And when yi is 0, this is 1. So this is 1 minus rho, which we know is right, that the probability of getting a 0 given rho is equal to 1 minus rho. Now take the other possibility that yi is equal to 1. So here yi is equal to 1, so you have just rho. And here yi is 1, so 1 minus 1 becomes 0, and so this term goes away. And then what remains is that the probability of 1 given rho is equal to rho, which is exactly what you expect. And this is what is called the Bernoulli distribution. So now our objective is to estimate the value for rho using maximum likelihood estimation. So what that means is that, let's say we did a coin toss n times and what we got was n1 number of heads and n0 number of tails, so that their sum is equal to n. And now using this data, this training data that we have, our objective is to estimate rho using the process of maximum likelihood estimation. So if we just go by intuition, rho should be equal to n of 1 divided by n. But as we saw in the case of the Bayesian parameter estimation, that we get a different result for rho. So let's see, if we follow the maximum likelihood estimation, what kind of estimate do we get? So now our job is to maximize the log likelihood. You know, the log likelihood, as we define, is this quantity, the probability of yi given rho. So here in this coin toss problem we don't have xi, so we just have probability of yi comma rho. We take a log of that and sum over all possible values of I. So our total log likelihood is equal to the log of probability of y given rho, which is equal to sum over all I log of probability of yi given rho, and this is equal to sum over I log of rho power yi into 1 minus rho power 1 minus yi. So now as we know that the log of a product is equal to sum of the individual logarithms. So now if we do that simplification, what we get is that our log likelihood is equal to log of rho times sum over I yi plus log of 1 minus rho sum over I 1 minus yi. So now this is fairly simple. Our yi can be 0 or 1. So this sum over all I of yi will be nothing else but the number of heads. Similarly, this will be nothing but the number of tails. So what we have over here is this is equal to n of 1 log of rho plus n of 0 log of 1 minus rho. So now what is our objective? Our objective is to find the value for rho which maximizes the log likelihood, right? If you remember, that is what we wanted to do. Our rho MLE, or the maximum likelihood estimate for rho, was the value for rho which maximizes the log likelihood of our problem. So how do you maximize? As you must have actually, as you must have learned in school, that the maximization or minimization happens at a point where the derivative of the function goes to 0. So now whether to know it's a maxima or a minima, you need to take the double derivative, but we are not going to go into those complications. So I will only take the first derivative, equate the result to 0 and use that to find the value for rho. So our rho MLE is that value of rho for which dou log likelihood by dou rho is equal to 0. Okay, so as I said, I'm not checking whether this is maxima or minima. I leave that to you. What I'm going to do is only to take a derivative and equate that to 0. So now you take dou LL by dou rho, that is simply equal to n of 1 by rho minus n of 0 by 1 minus rho, and you equate that to 0. So what you finally get is the MLE estimate, which is nothing but n of 1 divided by n of 1 plus n of 0. Fantastic. So we have found the maximum likelihood estimator for our rho, which was a probability of getting ahead. And interestingly, what we find is that this is exactly same as what we would predict from intuition. Okay, so without doing any math, if you asked me what the result would be, that would be exactly equal to this quantity. So in other words, maximum likelihood estimation is generally our intuitive estimation for a particular parameter value. So now we are going to see a more general description of this method, and in particular we are going to see how to use MLE for regression as well as classification. So let's take regression first and see how to use MLE for regression. And here we are also going to learn about why a Gaussian distribution plays a very important role in machine learning problems. So now we are going to see how to use MLE for regression. So what is the meaning of regression? So regression means that you have some output values yi, which are related to the input values xi through some function g, which is a function of xi, which are the input values, and the model parameter values. And there is, of course, some error because no estimation is perfect. So this estimation g that we have of our output values will never be exactly equal to yi, and there will always be some error. So this is essentially a curve fitting problem. Okay, so given a value of xi, we are trying to predict what yi should be. So according to MLE, our rho MLE is equal to arg max over rho of the log likelihood, which is summation over I log of the probability of yi given xi comma rho. Now where does this probability come in now? Because given xi and given rho, this is a deterministic function. So obviously the probability has to come from epsilon I, which is actually the error term. So this probability of yi given xi and rho is nothing but the probability for the error. So this is equal to argmax over rho summation over I log of the distribution of epsilon I, because epsilon I is a continuous random variable, so we worry about its distribution. So now our job is to use an expression for f of epsilon I, otherwise there is no way to make progress. So we are going to assume that our epsilon I is actually distributed as a Gaussian, and this is where Gaussian enters into machine learning. So this is a Gaussian. So what does that mean? What that means is that this expression f of epsilon I is given by 1 by root over of 2 pi sigma square into e power minus epsilon I square by 2 sigma square. So we are assuming a zero mean Gaussian noise, and this is how its distribution looks like, and this sigma is the standard deviation of this noise. So now if you substitute this expression into here, then you can maximize this quantity quite easily. So now what do we get? The rho MLE is equal to arg max over rho summation over I log of 1 by root over 2 pi sigma square plus summation over I log of e power minus epsilon I square by 2 sigma square. So now as we can notice that this quantity log of 1 by root 2 pi sigma square is just a constant. As you change your error or whatever, this does not really change. So this we completely throw away. And now here log of exponential, this will again go away. And so what remains is arg max over rho of minus 1 by 2 sigma square summation over epsilon I square. Now once again this 1 by 2 sigma square is a constant, and so that goes away. And here if we have a minus and we are trying to maximize a negative quantity because this is obviously all positive. So trying to maximize a negative quantity is trying to minimize the quantity without the minus sign. So this is equal to arg min over all rho of summation of epsilon I whole square. And now what is epsilon I? Going back, epsilon I is nothing but yi minus g of xi comma rho. So now this quantity is equal to arg min over rho summation of over all I yi minus g of xi comma rho whole square. So this is exactly what is known as the least squares error term, or in short it is referred to the LSE, and this is exactly what curve fitting is all about. So we saw that if we assume that the error is a Gaussian distribution, our maximum likelihood estimation for a regression problem essentially leads to the least squares error, which is what we use for curve fitting problem. So sometimes this error function is also called the cost function or the loss function, as we are going to encounter in the machine learning literature. So this is how you use the maximum likelihood estimator for regression. We are going to see more details of this regression when we come to linear regression in later videos, but this is just to give you an idea about the mathematical machinery which is used in such problems. So now let's see how your MLE can be used for classification. So now let's see how the MLE can be used for classification. So now here, of course, the classification problem can be a lot more general and you can have multiple categories and so on. But for the sake of simplicity, we are only going to assume that our output yi is binary in nature. So output yi can either be 0 or 1, something like a coin toss. But unlike a coin toss, now we also have some input values xi. So basically, we now define a function gi, which is equal to g of xi comma the parameter values, and basically what gi represents is the probability that the output yi is equal to 1. Okay, so now in this machine learning problem, we are going to predict for a given input whether the output should be 1 or 0, but instead of saying definitely that it is definitely 1 or definitely 0, we are going to make a probability estimate. We are going to estimate the probability that the output is 1 or 0, and that is what our gi represents. So now this GI could be a logistic regression, could be SVM, could be even artificial neural networks or whatever. So here we are only focusing on the general framework for MLE when it is used for classification, and the actual application could be something very different. So for example, these classes 0 and 1 could represent a diseased and a healthy individual, a bank default or a loan payment, or fake news and non-fake news, and so on. So we are not going into the specific application in this video. We are only talking about the general mathematical framework of how to use MLE for doing classification problems. So now, like we had in the previous case, rho MLE is equal to argmax summation I log of the probability of yi given xi and rho. We can again write this as argmax summation over I log of gi to the power yi into 1 minus gi to the power 1 minus yi. So when yi is 1, this quantity reduces to gi, and when yi is 0, this reduces to 1 minus gi. So this is a compact way of representing the binary classification problem. So now we can again separate this out. So this can be log of this plus log of this, and for the sake of simplicity we also take a negative sign which makes argmax into argmin. So this is equal to argmin of minus summation over I yi log of gi plus 1 minus yi log of 1 minus gi. So this is what we try to minimize for our classification problem, and this whole quantity is our cost function now, and this is what is called the binary cross entropy. So this binary cross entropy is a very popular loss function or a cost function which is used in binary classification problems, irrespective of whether you are using logistic regression or ANN or any other kind of classification problem. So there are of course other loss functions also available which are used in some specific instances, but for a binary classification problem, this binary cross entropy is generally the default choice. And now you understand how we get this binary cross entropy from our maximum likelihood estimation. So this was a short introduction to maximum likelihood estimation from a general mathematical perspective, and in future videos now we are going to see how to apply it for specific machine learning models. So till then, stay connected.